Alright, so let's take a look at section 7.4 and 7.5. Let's take a look at natural logarithmic functions, and we're going to learn how to find the derivative of a natural logarithm function. So we're talking about y equal to ln of x. The same thing as ln of x is log with base e, x. And e is what we call Euler number, is approximately equal to 2.718. Okay. In this particular section, we're going to learn to develop and use properties of the natural logarithmic function. We try to understand the definition of the number e, Euler number. And we're going to learn how to find derivatives of functions involving a natural logarithmic function. Natural logarithmic function. So, if you take a look at general power rule, right? For antiderivatives of x to the n dx, it's equal to x n plus 1 over n plus 1, n plus c. In this case, n cannot be equal to -1. And when n is equal to -1 dx, then the power rule does not apply. So you're going to use second fundamental theorem of calculus to define such a function, right? Define 1 over x dx. Okay. Natural logarithm function is neither algebraic or trigonometric. It's a completely new category of the function. And if you take a look at the graph of the natural logarithmic function, the graph looks like this. This is what the graph looks like. And for this y equal to ln of x. And as you can see, the domain is from 0 to positive infinity. It gets infinitely close to y-axis, but never touches it. So the domain is from 0 to positive infinity. Okay. Domain is right here. And as you can see, it goes up and down on both directions forever. So the range is all real numbers, meaning from negative infinity to positive infinity. And when you look at the function itself, it's continuous everywhere. There's no gap, no jump, no breaks. And it's increasing from left to right. Okay. And also it's one-to-one relationship. We draw the vertical line, there's only one intercept. Only one intercept. As well as the graph is concaving downward. Okay. So that's some basic properties about the natural logarithmic function. And now let's review some of the basic properties of logarithm functions. So if a and b are positive numbers and n is rational, then the following properties are true. ln of 1 equal to 0, meaning pass through, graphically speaking, pass through 1, 0. And ln of a times b, the product becomes the sum. Becomes ln of a plus ln of b. ln of a raised to the n power. So again, you put the exponents in front. and it turned out to be n times ln of a. And the quotient ln of a over b, this is a quotient. Quotient becomes difference. It becomes ln of a minus ln of b. Okay. Let's take a look at how we use those properties to simplify the, or to expand the logarithmic expressions. Like ln of 10 over 9 becomes, the quotient becomes the difference. ln of 10 minus ln of 9. And second one, ln of the square root of 3x plus 2 is equal to, so first of all you turn this radical, square root of 3x plus 2 as exponential, so which is 3x plus 2 raised to the half. And now I put a half in front, half times ln of 3x plus 2. Okay, that's the final answer. ln of 6x over 5 equals ln of 6x minus ln of 5. So quotient becomes subtraction. Then the product becomes addition. So ln of 6 plus ln of x minus ln of 5. And that is how you expand it completely. Indeed, let's take a look at ln of x squared plus 3 parentheses to the second power over x times cubic root of x squared plus 1. So the quotient becomes subtraction. And now we're going to break down further. So the exponents goes in front. So 2 times ln of x squared plus 3. Now the product becomes addition, so ln of x plus ln of cubic root of x squared plus 1. Now we're going to simplify further. 2 times ln of x squared plus 3 minus ln of x. Now turn the cubic root as exponent, it becomes ln of x squared plus 1 to the 1/3. And you make 1/3 goes in front. So it's 1/3 times ln of x squared plus 1. Then you get rid of the square bracket. 2 times ln of x squared plus 3 minus ln of x minus 1/3 of times ln of x squared plus 1. That's going to be the final answer. The number e, what we call Iona number, e is approximately equal to 2.718. Okay. And e is, for the natural logarithm function, e is what we call the base. Okay. This is the base. E the base. Just like the common logarithm is like base 10, so like something like a log 10 becomes 1. If you switch back to the exponential expression, that should be base raised to the first power equal to this number 10. 10 to the first is equal to 10. The base for the natural logarithm is defined using the fact that natural logarithm function is continuous. It's 1 to 1, has a range of -infinity to +infinity. So it's defined by using 1 over x dx, antiderivatives. Okay. Or you can call that indefinite. It should be definite integral. Alright, so technically speaking, let's say one of E is defined Ln of E. Define using 1 of E, 1 over x, dx. And here you can just use another variable, t. If you rewrite it, it should be definitely integral 1 to e for 1 over t dt. They're equivalent, so typically they use t as variable to define the Ln number e. As you can see, function y equals to 1 over t. This is the graph of it. Then we're taking the definite integral from 1 to e. We'll try to figure out the area under the curve bounded by the 1 over t and x-axis, and this is x equal to 1, this is x equal to e. Okay, so the area is what we call Ln of e, which is 1. Okay. So letter E denotes the positive real number such that Ln of E equal to definite integral 1 over t dt from 1 to e, which is equal to 1. Okay. Then once you know Ln of E equal to 1, then you can use logarithmic property to evaluate natural logarithms of several other numbers. And they're just examples. I can easily find that through the calculator. Now let's take a look at the derivative of natural logarithm functions. The derivative is very straightforward. Derivative of Ln of x is equal to 1 over x. Derivative of Ln of u is equal to u prime over u. Okay. Then u be a differentiable function of x. Derivative of Ln of x equal to 1 over x. When x is greater than 0. That's a domain for Ln for natural logarithm function. Second one, derivative of Ln of u with respect to x is equal to 1 over u times du over dx. Du over dx, we call that u prime, so that's why it becomes u prime over u. Okay. Here u must be greater than 0. So let's take a look at following examples. I'm going to use differentiation rules to find foreign derivatives. So here, find the derivative of Ln of 2x. So in this case, we know that u is equal to 2x. So u prime is going to derivative of x becomes 1, so it's 2 times 1 equal to 2. So now rewriting as Ln of u. And based on the previous property, derivative of Ln of u is equal to u prime over u. So this is going to be u prime over u. U prime is 2, u is 2x. So cancel 2 and it becomes 1 over x. Okay. Second one, we have a Ln of x squared plus 1. So in this case, u must be equal to x squared plus 1. So u prime, derivative of x squared using the general power rule is going to be 2x. Derivative of 1 becomes 0. So eventually just 2x. So you rewrite this as d dx Ln of u, which is equal to u prime over u. So u prime is 2x, u is x squared plus 1. That's it. So the key thing here is figure out u. U is whatever inside the parentheses. Find u prime. Then you find the derivative. Third one, we're going to use product rule. So here we find the derivative of x times ln of x. So u is x. That means u prime is 1. B is ln of x. Then b prime. Then b prime is just going to be 1 of x. Now we apply the power rule, the product rule, u prime b plus uv prime. Then becomes ln of x times 1. And x times 1 of x. The final answer is 1 plus ln of x. Let's take a look at the last question. Derivative of ln of x to the third power. So now here you gotta use the chain rule. You're assuming u equal to ln of x. So u prime is 1 of x. So we're going to rewrite this as d dx. It's going to be u to the third. And apply the chain rule, should be 3u squared times u prime. Just replace u with ln of x and then u prime with 1 of x. Then you find the final answer. 3 times ln of x squared times u prime 1 of x. So we can have 3 times ln of x squared over x. And it's very convenient to use logarithm as assistance in differentiating non-logarithmic functions. This procedure, the process is called logarithmic differentiation. So let's take a look at the example how we utilize the property of logarithm to find the derivative. We call logarithm differentiation. Okay. Now we have a function y equal to x minus 2 squared over square root of x squared plus 1. So typically you can just use a quotient rule, since we learned quotient rule already to find the derivative. But for this question, we're going to take a look at using a logarithmic differentiation. So for logarithmic differentiation, first step, you're going to taking ln from both sides of the equation. And we're going to use some properties to simplify this expression. Okay, so let's expand it. Ln of y equal to the quotient becomes a difference. Put exponents in front is 2 times ln of x minus 2 times ln of x squared plus 1 to the half. So again, put exponents in front. And the y equal 2 times ln of x minus 2 minus half times ln of x squared plus 1. Now we're taking derivative on both sides of the equation. Derivative of ln of y becomes y prime over y. Just like the derivative of ln of u becomes u prime of u. It's identical scenario. So right here, again, you setting u equal to x minus 2 So u prime is just going to be 1. So here it becomes 2 times u prime over u. So 1 over x minus 2. And for second logarithm, setting u equal to x squared plus 1, and u prime is going to be equal to 2x. It's minus half times 2x over x squared plus 1. And let's simplify the right hand side really quick. Okay, let's do it here. So y prime over y just become 2 over x minus 2 minus, we reduce, cancel 2, it becomes x over x squared plus 1. Now the LCD on the right hand side is going to be x minus 2 x squared plus 1. So y prime over y, 2 over x minus 2 times x squared plus 1. Second one, you multiply x minus 2. Now they are like fractions with the same LCD. X minus 2 x squared plus 1. Expand it, we get 2x squared plus 2 minus x squared minus x times minus 2 becomes 2 plus 2x. Simplify the expression, so you end up with y prime over y equal to x squared plus 2x plus 2 over x minus 2 x squared plus 1. Now we're going to multiply both sides of the equation by y. Okay, cancel y. So y prime equal to, then y is equal to this. Alright, now replace y with that. So you get an x squared plus 2x plus 2 over x minus 2 times x squared plus 1 times x minus 2 squared square root of x squared plus 1. So cancel x minus 2. So we get a y prime equal to x minus 2 times x squared plus 2x plus 2 over square root of x squared plus 1. It just becomes x squared plus 1 to the half. Times that becomes x squared plus 1 to the 1 plus half. 1 plus half is 3 over 2. So that's going to be the final answer. Okay, if you use the quotient rule, you should end up with the same answer. Okay. And in the background, just solution of this. And derivative involving absolute values. So let's say if u is a differentiable function of x such that u is not equal to 0, then derivative of ln of absolute value of u is also equal to u prime of u. It's the same thing as derivative of ln of u. U prime of u. Let's take a look at the example. Find the derivative of f of x equal to ln of cosine of x. Okay, so in this case, u is equal to cosine x. So u prime, derivative of cosine x is negative sine x. So derivative of f prime of x, it should be equal to u prime over u. So negative sine x over cosine x. Sin x over cosine x is tangent x. the answer is negative tangent x. And that is pretty much it.